Yes.
So it says we're live on YouTube, but we're actually not yet. It's just setting up the things.
Okay.
So
is Hannah here?
Yeah.
Hi. Could you hear me?
Yeah.
Okay.
Yeah.
And you're panelist now, Ahmed. So
Okay. Hi.
Hi. Good morning.
Good morning.
Piotr?
Yes, I'm trying. Yeah, I'm getting there. You're host now.
Okay. So we do it as yesterday, so that only the hosts can share screen, and then I promote Hamed now, who's the first speaker to co-host for this.
Okay, and you co-host me, please, and you co-host Lars Anderson when he shows up.
It's fine. Yeah, give me a second. So
and I'll be right back.
Your co-host, so you should be able to share your screen now.
Okay, great.
Should I share the screen? Or?
Hannes is here. Good morning.
Good morning. Good morning, Maciek.
Good morning. Good morning.
Thomas, good morning.
Good morning.
Ahmed, good morning.
Morning. Thomas?
Yeah?
So should I share the screen or because the machine?
Yeah.
Okay, because the computer is it's doing something sometimes crazy things. So let me just try.
Yeah, take your time.
Hi everyone.
Hello, Piotr.
Hi Peter. Do you want to go for a walk this afternoon, or it's too cold?
It's too cold.
No, it's not that cold.
Well, send me an email if you want to, if you're interested.
Is this?
Could you see the screen?
Yeah, there's a black box on the right-hand side for some reason, but otherwise, yes.
What about now?
That's fine.
Is this fine?
Yeah, it's fine.
Okay. Okay.
Chat.
Good morning, Peter.
Morning.
You're sitting in Mauerbach or in Vienna?
On the outskirts of Vienna.
Okay.
Oh,
in your flat.
Yes.
You could be in Mauerbach. It's probably very, very pretty now, huh?
Yes, it's very pretty, but we don't want to heat the house for such a long time. And yeah, we feel more comfortable in winter in our.
So what do you do with the water then?
Well, the garden water is emptied in autumn, and the house is heated well up to so that it doesn't freeze. Yeah.
Plus 1 degree.
How much?
Plus 1 degree.
No, that would be too little, because then the walls freeze. So this is not the right thing to do. Okay. One has to, the gradient, so to speak, be such that actually the 0 point should be well outside, on the more or less on the outside of the walls.
Good.
So there is some heating necessary, but although these mild winters for a long time, I don't have to turn on this heating.
Mm.
This is actually the first week this winter where we have freezing temperature throughout the day and night.
Yeah.
So, what about you?
It's fairly cold.
Yeah, but where are you? Where are you
freezing.
sitting?
At night it was sometimes -14 or something like that.
In Warsaw, we have the same temperature, -14.
We get the cold from you.
Usually, yes.
In my apartment, the heating is on, but I am still cold, just it's not easy to sit, just.
This is because the poles will turn off, go away from coal, yeah? What kind of heating do you have?
Central heating.
Yeah, but what kind of? What does the center? What is this? What does it come
I think
from?
the heating is produced by this power plant, and this is, as far as I remember now, it's the Swedish one. So I don't remember.
So what is it? Is it
but
gas?
of course, it is coal. Of course, it is coal.
Coal, right?
Yeah.
You should get rid of this.
I'm not sure. I'm not sure, because what will you get instead? You know that now in Sweden they have problems. They switched off the power plant, the nuclear power plants, and they have no power.
Do you have power plants, atomic energy?
So this is a big problem in Poland, because they plan since 30 years and nothing happens, and that's very strange. This is politics,
Well, in Austria, it's such that we don't have atomic power plant. Well, we have one, but which is a museum by now. But we import electricity from atomic power plants. That's the logic.
May I address a minor problem? I have a big black patch on the screen. Where does it come from?
Yes.
Is it my screen or is it universal? Now
yes, it's from you, Sweaty. It seems.
No.
Okay.
Okay.
This is on the screen of Hamed. This was on the screen of Hamed.
Sorry. And now
Wherever
see.
you put your mouse cursor, it shows a big black block below it for some reason.
Okay. So
just move the cursor to the side if possible, and don't indicate too much of the.
Okay.
Possible.
John?
It's not good. Okay.
Helmut, did you say something?
Yes.
Uh-huh.
Do you have an idea where the next meeting takes place, or do you want to do it electronically again?
Well, I'd like it to do it in person if you can.
Yes.
Do you have a suggestion where we do it?
No. I mean,
should we just meet after the second hour for a few minutes, the organizers, to discuss this?
I have nothing to offer. I just wonder.
No, but so just to discuss what we're going to do.
Okay.
Okay, good.
After the last talk.
After the last talk, yeah.
This morning, yeah.
Right, yeah.
Yeah, there's a break and.
But the breaks don't seem to work, right? So let's start the session and let's discuss it later.
Okay.
So shall we start, Piotr? Yeah.
Yes,
okay.
Yes, of course.
Yeah.
Go ahead, Maciek.
So good morning, everyone. It's freezing outside, but we are sitting inside in the cozy rooms. If we have a heating turned on, this is a morning session of the CRS meeting, and the first speaker is Hamed Pasega from Vienna, and he will be talking about cosmology with Masters Vlasov. So 15 minutes, Hamed. I give you 5 when you will be close. Take it away, please.
Okay, thank you, and good morning, everyone, and thank you very much for having me. this Saturday morning to present my recent work on Bianchi cosmologies with massless loss of matter, which is available on Web, and it is going to appear soon in CQG. So let me start right away with the motivation. I'm interested in mathematical cosmology, and one of the main goals of the mathematical cosmology is to understand and determine the future fate of the cosmological models. And by cosmological models, I mean the model that consists of three essential elements: cosmological model, cosmological spacetime, theory of gravity, and matter model. So in this talk, I'm going to consider Bianchi spacetime, which is a subclass of spatially homogeneous spacetimes. I consider general relativity with vanishing cosmological constant, and I take loss of matter as matter model. So why I do that? Because there are some observational challenges in the concordance model of cosmology, which suggests that we may abandon the assumption of isotropy. On the other hand, I'm interested in loss of matter, which is a reasonable matter for describing the stars, galaxies, or even cluster of galaxies on larger scales. It models the matter, and it assumes that the matter doesn't have collisions, so it's reasonable. And on the other hand, I'm interested in the vanishing cosmological constant case, because as it pointed out by Zoe 2 days ago, things are less better in the case where cosmological constant is present. So then show the future attractor of the massless Einstein velocity system for Bianchi types 2 and 5. In the Bianchi cosmologies, the Einstein equation is reduced to ODEs, but the velocity equation remains a PD in general. If one assumes forward symmetry, then, for example, the locally rotational symmetry, abbreviated by LRS, then future attractors could be found by dynamical system approach globally. And there are lots of work in this direction with perfect fluid. And for example, the classic textbook on this subject by Ellison Wainwright. But also there are some works with velocity of matter initiated by Randall and Todd in 1990. But otherwise, one has to assume small initial data if one doesn't want to assume forward symmetry assumption. But nevertheless, one can determine the decay rates with this approach. There are some results with massive velocity of matter on Bianchi type 1, 2, and 7 and 6, 0 by Nungesser, and Bianchi type 5 by Anderson and Nungesser. So the massless case is more challenging because we have a slower decay rate in the course of the expansion of the universe. So my proof is a little bit different. I used energy method and bootstrap argument, which go most of the time hand in hand. So Bianchi spacetime is a four-dimensional Lorentzian spacetime, which is globally hyperbolic and could be written as a warp product of an interval and a three-dimensional simply connected Lie group, which admits a left invariant frame, which satisfies the commutation relations where Ci, J, K are structure constants. And by choosing the appropriate frame, the left invariant frame and its dual are time independent, then one can write down the Lorentzian metric in this form where Gij is Riemannian metric and it's time dependent. So the important properties is that one can classify Bianchi models by classifying the structure constants of the Lie algebra, which could be written uniquely in the given form, where epsilon is the Levi-Civita symbol and n is the symmetric constant metrics, and ai are constant. So by a unimodular transformation, this constant matrix n could be diagonalized, and we have the three eigenvalues n hat 1, 2, and 3. So therefore, Bianchi Bianchi models could be classified into two classes, A and B, in terms of the constant A. And in Bianchi class A, we have these different types, 1, 2, and so on. And in Bianchi class B, we have Bianchi type 5 and 6H and so on. So I'm considering Bianchi type 2 and 5. And you see the eigenvalues of this matrix N. In Bianchi type 2, the only non-vanishing constant is N1, and these eigenvalues could be normalized to 1. I'm going to make a remark on Bianchi type 1. And on the right-hand side, you see different spaces. There are 7 spaces, and there is also another space S2 cross Euclidean, which corresponds to Kontowski-Sachs model. So as you already noticed, these are 8 different geometries in Thorsten's classification. So let me make a final remark on Bianchi. It is usually assumed in mathematical cosmologies that the space should admit compact Cauchy surface. If so, then the only Bianchi types 1 and type 9 admit compact Cauchy surface. We therefore usually consider locally spatially homogeneous space. However, this doesn't enter my calculations. Otherwise, there is no need to prove the stability of Bianchi type 5 because of the most of rigidity theorem, which says that 2 compact hyperbolic spaces are isometric up to global scaling factor if they are homomorphic. So let me introduce the philosophy matter. Fortunately, Leo introduced this yesterday. This matter modeled the collisionless kinetic gas, and they are modeled by a distribution function f, which is defined on the mass shell, and in this case, the mass is 0. So to this distribution function, one can associate an energy momentum tensor, which is given there. So the important assumptions here is that F inherits, so to speak, the symmetries of a spacetime, and has therefore the particular type on the right button. The second assumption is that I assume that F has compact support. And then energy density, energy current, and spatial part of the energy momentum tensor are given by these formulas. The point is that the trace of S is equal to energy density. And finally, the transport equation or Vlasov equation or collisionless Boltzmann equation is given by this formula, where gamma bar is the connection coefficients with respect to the Lorentzian metric in the left invariant ray. So then Einstein-Vlasov takes the following form. The first equation is the Hamiltonian constraint. The second and third one are evolution equations for trace part and trace-free part of the second fundamental form. And the fourth equation is the Vlasov equation, where omega ij are Ricci rotation coefficients. So H here is Hubble parameter, which is minus 1/3 of trace of the second fundamental form. Is positive because the universe is initially expanding, as we assume. And we define the Hubble normalized parameter by capital sigma, where sigma is the trace-free part of the second fundamental form. And then we define for the Hubble normalized parameter, the sigma plus minus. So omega is density parameter, Q is the deceleration parameter, and I also introduce the normalized, Hubble normalized Ricci tensor. So to this Einstein equation, one should couple the evolution equation for the curvature term, which is connected to the constants of the Bianchi types. So in the first attractor, I call generalized Collins-Stewart solution, and it's observed that in Bianchi type 2 by Keller and Hasler, that in Bianchi type 2 with LRS assumption, massless collisionless particles have the future attractor, and it's anisotropic. So we have the dynamical variables, So this N1 here corresponds to the curvature, and it corresponds to the non-vanishing eigenvalue of an N. So for the proof, I had to assume the reflection symmetry. It corresponds to the diagonality assumption by assuming that the distribution function initially has the following symmetry, and first and second fundamental form are diagonal, then the energy momentum tensor are diagonal, and so this symmetry is preserved by the evolution of by the evolution equations for all time. And the second attractor is the mill universe, as we have seen this already. It's a class of FLRW model with negatively curved space-time spatial part and with vanishing energy density. So in the left invariant frame, we have this particular form of the metric, and the variables, dynamical variables, are these following. So as we have seen in the talk by Zoe, this universe is non-accelerating or non-decelerating. So let me quickly say the theorem considers a smooth solution, initial data G sigma F for the massless Einstein-Vlasov system with reflection symmetry, Bianchi type 2 symmetry. Then if we assume that this value sigma plus minus 1/5 and so on, they are small, that is, we are a little bit away from the GCS solutions, then we could show the following estimates, and we show that this model is not only stable but also asymptotically stable, and corresponding result for Bianchi type 5 is the same, where I don't assume the LRS, and I show this generally with this estimate rates. So the proof is based on bootstrap argument. So because we assume that these values are initially small, we could assume that on a small interval t, not in capital T, we have the following decay rates. And if one could show that, or if one could improve these bootstrap assumptions, meaning that if one could show that they have faster decay rates, then by continuation criterion, one could show that capital T is infinity. So I do this by shifting the system and linearizing the system around the attractors, by the shifted parameters denoted by hats. So the last equation here is the evolution equation for the curvature, and I highlighted, so we have the corresponding result also for Bianchi type 5. I highlighted the bad terms, the critical terms, energy momentum tensors. So the essential proposition of the work is to estimate, to get good estimate for these energy momentum tensors. And we follow two different strategies. First, we look at the evolution equation of the energy momentum tensor, where the velocity equation enters directly, and we see that we have the bad term Yij, but if we assume reflection symmetry in the particular type of Bianchi 2, this term vanishes and one can show the results. On the other hand, for the Bianchi 5 type 5, we take advantage of the characteristic curve of the velocity equation, and one could show that the momentals are asymptotically constant. And since the distribution function has initially compact support, one could go to an spatial orthonormal frame and show that the energy density decays as t to the -4, because distribution function is constant along the characteristic. So then we define energy functions. Simple, they are simple, and in terms of the perturbed variables, and by introducing two constants C1, C2, or D1 into D1 and D2 in different types, and then one eventually shows that they decays, and the square root of this decays gives the estimates of the theorem. And so I think I'm already running over time. So let me just mention that with the same method, we showed in a joint work with David Feynman and Gernot Heissel the isotropization of the slowly expanding spacetime. And let me also say that this method couldn't work for Bianchi type 7, although they are almost, I mean, one expects that it should work because it corresponds to Sol geometry, and Bianchi type 2 corresponds to new geometry. But I wasn't fortunate to show that. So I leave you with this last slide, and thank you very much for your attention.
I'm muted. Thank you very much. I will clap for everyone. So we have some time for questions.
So, Hamed, can you explain again why you're using Bianchi 2 and 5? Why not the other ones? Maybe you explained this, but I just missed the point.
No, I mean, the other Bianchi types are, I mean, for the massless case, there are, in this approach, I know just one work which we did and another group. And so Bianchi type 5 is the easiest case in class B, and the easiest case in Bianchi type A after type 1 is the type 2. So that was the reason, because they are easier.
Okay, but so the equations become more complicated. That's the point. If you allow the
I think the point. I'm sorry. The point is that these components of the energy momentum tensor, they are too critical. For example, in type 6.0, I wasn't fortunate to get a good decay rates for them. So this.
So you've tried the other models and they just don't work well. That's the problem. There are technical difficulties.
Yeah, exactly. So 6.0.
And similarly for this symmetry hypothesis, if you drop this symmetry hypothesis so that you get some current, then you're in trouble. Is it?
Exactly, for the Bianchi type 2, exactly. So Bianchi type 2 was also critical if you drop the LRS, so locally rotational symmetry.
And as usual, this is only to the future, right? So who knows what happens for small t?
You mean past direction?
Yeah, right.
I think it's very complicated. But yeah. I guess in Bianchi type 5 it's easier. It should be Krasner, I think. And for Bianchi type 2, I think it should be tau, if I'm not mistaken. But I was concentrated in
sure, yeah, okay. Just thank you.
Okay, thank you.
May I ask a general question? In this book by Ellis and Wainwright, they treat the Bianchi models as dynamical systems, as you did, and there are a number of flow pictures towards the attractors and so on. Is that possible for what you have been doing? How the attractors are approached in the space of the dynamical variables?
So as I said, they approach the attractors in infinite times. So I'm not using the dynamical system approach. For dynamical system approach, as I said, you have to assume 4 the symmetries. For example, LRS, or I mean, they assume more symmetries, particular form of the distribution function and so on, because otherwise the dimension of the variable space is very large, and one cannot do the dynamical system.
May I ask on what you display now? This the G, the diagonal,
yes.
with this exponents of t, is that correct? Is not yes. one of them at least negative? Is it 2/3, 4/3, 4/3? At least in the Bianchi 9, and sorry, in the Bianchi 1.
Yes.
There should be one exponent be negative.
I think you're thinking of Krasner models.
Yeah, that's right.
Yeah, but the metric is Riemannian. It could be, and it's a covariant version of the metric. So the Gij down. So it couldn't be minus. I mean, the publish couldn't be minus.
Mm-hmm. Mm-hmm.
So the inverse is the minus 2/3, minus 4/3, and so on. And
I think Peter's point was that this is not a Bianchi. Yeah, Bianchi one would have different exponents than this one's,
Yeah,
right?
yeah.
So
exactly.
yeah.
But that's Bianchi too, right?
Yeah, there's Bianchi too. So
Yeah.
Uh-huh.
And it's the future attractor. So in Bianchi type 1, the future attractor is isotropic.
So that then all direction expanding, yeah, all direction
Expand
expanding.
and with different rates.
Yeah. Mm-hmm.
In general.
Okay, thank you for discussion. I think I don't see any questions in Q&A or in the chat. So let's thank Hamid again. Thank you very much. And we move on to the next talk. Quentin, can you try sharing your screen? Yeah.
Is it okay?
Okay, perfect. Okay, so I give you 5 when you will be approaching 15 minutes if you want to have some discussion.
Okay.
So next speaker is Quentin Vineron, and he will be talking about the non-Euclidean Newtonian limit of GR. Please take it away.
Thanks, and good morning, everyone. And I thank the organizers for the invitation to this conference. So, as you said, yeah, I will present my work on the definition and the construction of a non-Euclidean Newtonian limit of general relativity. This work is mostly motivated by cosmology, where Newton's theory is often used to construct cosmological models. But these models have necessarily an Euclidean topology, which is required by Newton's theory, which corresponds to a restriction with respect to general relativity. So in this sense, it would be interesting to define a theory which is locally equivalent to Newton's theory, but allows for non-Euclidean topologies. We would call such a theory a non-Euclidean Newtonian theory. We can already give an example of such a theory by taking the Poisson equation and changing the metric to feature a non-zero Ricci curvature. So for instance, if we take it to be proportional to the scalar curvature, we would allow for either spherical or hyperbolic topologies. With such a Poisson equation on scales small in front of the scalar curvature, this Poisson equation would reduce to the flat Poisson equation, and we would have a non-Euclidean Newtonian theory as I defined here. The problem with this approach is that it's purely heuristic and not justified from general relativity. And in this sense, it would be interesting, and we want to derive the non-Euclidean Newtonian theory from a limit of general relativity. So if we choose to adapt existing limits, there are many choices because there are many ways to define Newtonian limits. And in this work, I choose to adapt a well-defined limit, which is a limit of a one-parameter family of solution of the Einstein equations, which is called the geometrical limit. This limit is a limit from a manifold equipped with a Lorentzian structure to a manifold equipped with a Galilean structure. I will present precisely what are those type of structure, but basically they are invariant under Galilean transformations. This limit was introduced by Kinsler and Dotcourt, firstly, to derive the Newton-Cartan theory from general relativity, and later by Ehlers to define his frame theory, which is a generalization of general relativity and Newton-Cartan. So from this choice of limit that we want to adapt, we can refine the definition I gave for a non-Euclidean Newtonian theory to be a theory having non-Euclidean spatial topology and defined on a Galilean manifold. In this sense, the Galilean invariance is taken as a fundamental principle of Newton's theories, whatever the topology we consider. So I will first define and present what are Galilean manifolds and the Newton-Cartan theory, which is defined in such manifolds. we will then see how we can construct a limit from a Lorentzian structure to a Galilean structure. And we will then suppose that this Lorentzian structure is solution of the Einstein equation, which will give us the non-Euclidean Newtonian limit. Okay, so Galilean manifolds, these are four-dimensional manifolds, which are equipped with a Galilean structure, which is composed of a space metric, which is a rank-free symmetric twice contravariant tensor, which I denote H here, a time metric, which is a closed one form denoted tau, such that they are orthogonal, and a connection which is compatible with those two metrics. Those two metrics are invariant under Galilean transformations, and they define what we can call an absolute space and an absolute time in the manifold M. In this sense, this corresponds to the Newtonian picture of space-time. So the Newton-Cartan theory is constructed on such manifolds, and instead of and relates the matter content with the space-time geometry of the manifold. This can be in the same way than general relativity.
Question, Quentin?
Yeah.
I mean, surely this Galilean invariance, this is something you have to impose on top of it, right? I mean, H and tau have to be invariant for, that's an extra assumption. It's not automatic at this stage.
No,
additional.
Actually, if you, if you analyze Galilean transformations, you can show that they let invariant such a tensor here and such a one form here. And so you take those one form so that, yes, as you said, so that they are invariant under Galilean transformation. But no, it's automatic. I mean, it's Galilean transformation once you assume that your spatial coordinates corresponding to those Galilean transformation corresponds to the R with respect to the space metric H.
Well, what I mean is, if you take your H to be a metric on a sphere, then of course it's not going to be. I mean, Galilean transformations are normally translations and rotations, right? So if you take your H to be a metric on the sphere, it's not going to be an invariant under Galilean transformations, unless you understand them differently.
It's purely local. It's not.
So it's only at the level of the frames or something like that. You mean the rotations or? Yeah.
Those Galilean transformations. It's on a frame on just one tangent space. So it's purely local. You have one.
So Galilean transformations only mean rotations in the frame or something like that.
Yeah.
Okay.
I don't know if I'm clear, but.
Okay, thanks.
Okay, yeah. Okay, so Newton-Cartan theory, as I said, relates the matter content of the manifold M here with its space-time geometry, which can be seen with this second equation, which feature at the right the matter density and the left the Ricci tensor of the Galilean structure, the Galilean connection. If we take those equations and we spatially project them, and firstly suppose that we have an isolated system in R3, then we end up with the classical Newton equations, which instead of relating geometry with matter, they relate a gravitational vector field with the matter content. If instead of supposing an isolated system, we suppose an Euclidean compact topology, so it's necessarily Euclidean because the spatial curvature induced by those equations, so the curvature related to the space metric is the Ricci curvature is necessarily 0. Then you end up with the same equations with additional terms related to variable h, which corresponds to the expansion rate of the compact space. This variable is a fundamental field appearing in Newton-Cartan. And as the non-Euclidean Newton theory will be a sort of generalization of this Newton-Cartan theory for non-Euclidean topologies, it will feature this expansion rate, which threatens the approach as we will want to apply this theory, as I said, for cosmological models. So Newton-Cartan was first constructed from Newton's theory by Cartan in 1923, but it was later derived from general relativity by Dotcourt and Künzle, using this construction of a limit from a Lorentzian structure to a Galilean structure. When we take a Lorentzian metric and assume it can be decomposed into Lorentz series of a parameter E, which is 1 over C square, such that the contravariant components at leading order corresponds to the space metric, and the covariant components corresponds to the time metric. At leading order, the coefficients of the Lorentzian connection become if we consider this expansion, become the coefficient of connection, which is compatible with the two metrics and is a Galilean connection. And we can also show that the Fourier tensor of the Lorentzian connection becomes at leading order the Fourier tensor of the Galilean connection compatible with H and tau. In this sense, a manifold which is equipped with such a Lorentzian structure at leading order becomes a manifold equipped with a Galilean structure. Because this Galilean structure is derived from a Lorentzian structure, it is constrained by this equation, which I recall was the third of the Newton-Cartan equation, and when spatially projected, corresponds to the conservation of vorticity. This is a purely geometrical constraint. But what is really important is that there are no more constraints on this Galilean structure, and especially there are no constraints on the spatial curvature of the space metric of the Galilean structure and its spatial topology. Additional constraints, especially on the curvature, will come only from the Einstein equation. So let's consider this Einstein equation and take the leading orders of the Einstein of this equation on the left-hand side, which will give us what are the leading orders of the stress energy tensor as function of the Galilean structure variables. We can then show that this stress energy tensor needs to feature a -1 order, which is proportional to the space curvature, scalar curvature of the space metric, and 0 order, which feature 2, for now, unknown terms, a variable E and a vector Q, which by analogy with the usual decomposition of the stress energy tensor can be called a heat flux, and again by analogy, an isotropic stress, which is proportional to the Einstein tensor of the free curvature. I forgot to tell that the had variables are related to the Galilean structure. So for now, because E and Q in this limit are unknown, and especially we don't know the relation with the matter density, the equations at leading order are not closed, and we don't have the non-Euclidean Newtonian theory we want. For this, we need to suppose what is the full order of the stress energy tensor. We can first take the standard hypothesis for the limit, which is to assume that we have the usual dust stress energy tensor, dust form for the stress energy tensor. This hypothesis was made by Künzle, Dotcourt, and Ehlers, and leads to a leading order, which is proportional to the density, implying that E can be associated to rho, Q to 0, and the free curvature is equal to 0. We can then show that we retrieve the second Newton-Cartan equation, which I will not detail in this presentation. So this standard geometrical limit, to my knowledge, there is no study on of the existence of such a limit for general solution of the Einstein equation, but only for specific solutions, and this was done by Ehlers in 1997. But what is really important here is that once we make this assumption here, then the spatial curvature is necessarily 0, implying that the topology of the spatial section related to the Galilean structure is necessarily an Euclidean topology. It's not what we want, because we want spatial sections that have non-Euclidean geometry. So we see that it's not possible to take this assumption, and we need to impose at the limit that the curvature of the space metric is non-zero, implying that we are allowed to take to assume non-Euclidean geometries. As I said, this is not compatible with the usual form of the dust tensor. And actually, because there are these additional leading order terms depending on the curvature, we need to add an additional term in the dust stress energy tensor, which at leading order will feature those two curvature terms. These leading order terms can be interpreted for the first one to be an energy curvature proportional to the space curvature, and an anisotropic stress curvature for the second one, which is proportional to the Einstein tensor of the spatial curvature. But once we see that from this, if we want non-Euclidean topologies with this limit, we need to add a term. The limit is still not closed because we don't know the relation between E and the density rho. So we need to assume, as with the usual the standard limit, what is the full order of this additional required term. But before doing this, we need to understand why it is here, actually, because we never considered here before. So we can follow this line of interpretation by saying that adding this term in the dust stress energy tensor corresponds to a generalization of the stress energy tensor for a dust fluid, which in particular allows for a non-Euclidean Newtonian limit. If we follow this interpretation, then the fluid, which is given by the 4 velocity u, needs to be geodesic, because it's called a dust fluid, which needs to be implied by this conservation equation, even with this second term. So from this, we can make first guess to what should be this second term at full order by taking the knowledge of the standard limit and assume that E is equal to rho and Q, the heat flux, is equal to 0, and we associate tau, the time metric, to be the 4 velocity of the fluid as made with the standard limit. We would get in this extrapolation this form of the stress energy tensor, which we can check leads to the geodesic equation. The problem is that there are many more guesses, many more extrapolation we might propose that leads to the geodesic equation and leads to the same leading order terms. And the problem is that the non-Euclidean Newtonian theory will depend actually on this extrapolation. So we are not able to give this theory for now, and we just know that we have to add an additional term in to have it in the stress energy tensor. So during this presentation, I proposed a way to define a non-Euclidean Newtonian theory from a limit of general relativity, a geometrical limit. We saw that if we want this limit to feature a non-Euclidean special topology, it requires an additional term, this dust stress energy tensor, which still needs to imply the geodesic equation at full order with the conservation equation. The perspective would be to study further extrapolated stress energy tensor at full order and try to find the right one, the most physical one, if there is one, which would finally give us the form of the theory at full order, which would be a powerful tool to study the effect of topology in a structure formation and expansion. So thanks for listening, and if you have any questions, please.
Thank you. Thank you very much for the presentation. For everyone. We had some few minutes for questions. So anyone, you can ask questions in the chat in the QA session, in the QA section also.
Maciek, I have a remark about this.
Yeah.
May I?
Sure, please.
Okay, so I want to say that you included also cosmological constant, but in the case of when you think about non-relativistic limit of de Sitter, because you know this is roughly non-relativistic or Newtonian limit of Minkowski, roughly.
It's not actually. It's not Minkowski.
I know, but
yes.
Let me say, but if you start with another symmetries with de Sitter, there is another opportunity to pass to the non-relativistic limit, which is called Newton-Hooke spacetime. And this means, and this was discussed a little yesterday with some equations, but the geometric, let's say, structure is this Newton-Hooke spacetime, and then you have a Galilean analog, which is also sometimes called Newton-Hooke. So I just want to address that maybe it is nice to understand also these structures. And this is just a remark.
So if I understand it correctly, I mean, this had to do with the way how you go with lambda to 0 when c goes to infinity, right?
Exactly,
and so
exactly.
In your equation, would this mean that
it would be not all the epsilon square, but rather epsilon in this limit?
Do you have a feeling what would happen with your equation? Would lambda just vanish from the equations, or what?
Here,
yeah.
For this not actually this does not change. No, this does not change anything, and the discussion. Actually, this lambda goes into this e here.
So this is it not exactly what you were referring to, Jacek? That you take lambda going to 0? Is Piotr there? Maybe he can just confirm. Piotr Bizon? No.
Yes, what Jacek is talking about is that lambda times c squared goes to a constant.
And in this language, is this what happens or not?
I don't know the relation to
Einstein,
to Newton-Cartan theory. So
here this does not go e square times lambda does not is not a constant at the limit, because the limit of the covariant components of the space-time metric is minus it's just an epsilon here, is a -1 order actually, and so this epsilon cancels with the epsilon which is here in the metric. So actually it's an epsilon and not an epsilon square.
Yeah, but you keep lambda constant, right? When you take
lambda is constant, yeah.
So
yeah, lambda
it's a different limit.
actually, because lambda is also featured in Newton's theory. I just keep it constant. For instance, here you end up with this equation, which is purely Newtonian, where the same lambda features actually. So yeah, lambda doesn't change, just this changes.
So in this limit that Piotr mentioned, it will just vanish from the equations, probably.
I suppose, yeah.
Now, so you took the geodesic equation, some kind of fundamental equation, because maybe it's the equivalence principle or something like that. But maybe maybe there's a more natural, there's another natural equation which could be thought of in this context. I have no idea, but what? And
actually, another equation I would like to preserve, but I'm not sure, is the mass conservation in the form of nabla applied to rho times u. And for instance, this form here doesn't preserve necessarily this conservation equation. But I'm not sure at which point we should necessarily keep this conservation of rho and not a conservation of rho plus rho r. For the geodesic equation, it's sure, but yeah, I think there are more
some options here. Thank you.
Okay, thank you. So thank you for nice presentation. We move on with our schedule. So Hannes, if you could.
Yeah.
Okay, cool. We see you. It's the question whether we will see your presentation. Perfect. Okay. Okay, let's start with another next speaker. And Hannes Ruther will tell us about DFGHG. And hopefully he will explain what that means and its application to spherical black hole excision. So please, Hannes, I will give you 5 when you will be closing to the
Okay, thank you very much.
please.
So the applications I will talk about here are presented in this paper that we recently put on the archive, and the actual implementation of these new applications we have were actually worked out by Maitreya Bhattacharya and David Hilditch, who based their implementation on my initial implementation of the dual foliation GHG that I will explain in a minute. Yeah, my implementation in the numerical relativity code MAMS. So what is GHG? So GHG stands for the so-called generalized harmonic gauge formulation. And the generalized harmonic gauge is given by this first equation here. That's a choice of coordinates that you can make, where you specify a gauge source function h, and you can freely specify it, but it must be a function of your coordinates and the metric components, but importantly, not a function of the derivatives, of any derivatives of your metric. And when you make this gauge choice, you can formulate your Einstein field equations as this kind of curved space wave equation. So you have the curved space wave equation operator on the left-hand side, acting on the metric component. On the right-hand side, you have some source functions which involve, among others, the gauge source function from the generalized harmonic gauge. And the rest of the equations are not important. And then for numerical relativity, we use a special first order reduction of this that was presented in this paper I give here. And that gives you then evolution equations for your metric components and the reduction variables pi and phi. And then when you do this first order reduction in a sensible way and you add...
Sorry, can you say again what phi is?
Phi is a reduction variable for the metric. So it represents the derivative of the metric, the spatial derivative of the metric. So pi corresponds to the time derivative of the metric, and phi the spatial derivatives.
Okay, thanks.
Okay. And yeah, we like this formulation because it is symmetric hyperbolic, and it has constraint damping, and both of these things are very important in numerical relativity because you always have small perturbations and constraint violations due to numerical roundoff, and you have to keep those under control. So that's why we like this formulation very much. However, you see, we have only little control over the gauge in this formulation. So you see, we can specify this gauge source function h, but we would like to have more control over our lapse and shift, which I denote here with the symbols alpha and beta. You can actually write down the evolution equations for lapse and shift in terms of your gauge source functions, but this is still then very hard to get control over the lapse and shift directly. And that's why we use the so-called dual foliation formulation of the generalized harmonic gauge. So what is dual foliation? So in the dual foliation formalism, you basically work with two foliations, two sets of coordinates. And we denote them with capital letters for one set of coordinates and with lowercase letters for the second set of coordinates. And we also underline indices that correspond to a basis that is associated with the uppercase foliation. and no underlining for the lowercase coordinates. And in our applications, the uppercase coordinates, they will be associated to our tensor bases, whereas the lowercase coordinates are actually the coordinates along which we evolve. And those two don't necessarily are the same.
But so there are two times functions, or there's only one time function, and this underbarred coordinates correspond to the tetrad decomposition or something like that?
So we really have two different time coordinates.
Thanks.
So, and in this picture here, basically your tensor bases would correspond to coordinates on the blue hypersurface, and the time direction along this blue vector arrow, and the normal vector we denote here with a capital N, but the evolution is done along this red arrow, which is a lowercase n here. Okay, so maybe to give you more help to understand what's going on here. So in the standard GHG formulation, we would have evolution equations where the time derivative is with respect to the uppercase coordinates, and also the tensor basis of the metric is associated with uppercase coordinates. And now in the dual foliation generalized harmonic gauge, the tensor basis of our metric is still the same, but the time derivative is now with respect to a different t. Yeah, with respect to different time coordinates. So for the TT component, the equations would look like this. So you see G has tensor basis with uppercase time coordinate, but it's evolved along lowercase coordinates. And I don't give you here the equations or how you make this transformation from standard GHG to dual foliation GHG. You can look that up in this paper I cite here. And basically you do the same also for your spatial derivatives. So what was a spatial derivative with respect to uppercase x becomes now a spatial derivative with respect to lowercase x. And how does this help us? So it turns out that hyperbolicity actually depends on the tensor basis of your objects. And because the tensor basis of our metric isn't changed, the symmetric hyperbolicity of our equations is retained. And these working coordinates, they can now be freely specified, and we can choose a good lowercase gauge as we need it.
May I ask something?
Yes.
The working coordinates are the coordinates as usual, is it? I mean, the space-time coordinates. And then you have these other coordinates. What's the relation between them? There must something be there which fixes the relation between these things.
Yeah, so
is it a frame or something?
Yeah, so we have to specify some coordinate transformation between them. And basically by choosing this coordinate transformation, so choosing this coordinate transformation is exactly what you have to do to get a good gauge. So probably it will become more clear when I show you some applications. But yeah, both sets of coordinates are of course space-time coordinates. They are just used, so the two different sets of coordinates are just used for two different things.
But you're not worried that the one coordinate system goes there and the other completely off? I mean,
no. So I mean, we evolve only at one point, And at every point, what we actually have to do is we have to specify the Jacobian. And as long as we have the Jacobian at every point, we can always translate between the two.
That's specified by hand, or is there a rule, or how do you do that?
Yeah, so specifying the Jacobian is basically what you have to input into your equations.
Okay.
Okay, so in this talk, I want to talk mostly about applications to a black hole excision. So let me do a small excursus to black hole excision. So you have your numerical grid here, and then on this numerical grid, you might have an apparent horizon, that is a red curve here. And then inside the apparent horizon, you cut out a region from your numerical domain because you don't want to handle the singularity. And basically then this excision must be somewhere inside the apparent horizon. And because nothing should come out of the black hole, the idea is here that you don't have to specify any boundary conditions on this excised region, because it won't, whatever you specify wouldn't even matter for the outside space-time. And here I have a different image visualizing this in spherical symmetry. So this dashed line is your apparent horizon, and this red line would be the expansion of outgoing null geodesics. And at one point, this expansion becomes 0. That is exactly your apparent horizon. And then what you also have to deal with, and your excision boundary has to be somewhere inside. And then another complication is that there's also the incoming coordinate light speed. And basically, when the coordinate light speed that is coming into your numerical domain, not into the black hole, when that is negative, then information is only flowing into the black hole region. If it's positive, you actually have something coming out. So your excised region also has to be in a region where this speed is negative. And you see, as I show you in the sketch here, those two positions are not necessarily the same. And that's kind of problematic. Another problem that you have to deal with is that, because your space-time can be dynamic, it could happen that your apparent horizon moves inside here if you choose bad coordinates. So you have to keep the apparent horizon outside, and you have to control this incoming coordinate light speed.
Why do you want to keep the? Why do you insist on the apparent horizon?
What do you mean? So if I specify,
well, the apparent horizon is just an apparent horizon; it has no significance other than that. Why do you want to keep it outside? I mean, who cares? I mean, I think that the important thing is your information flow, right? Maybe the blue line.
Yes. So it could also be, I mean, information flow is not the only thing you have to keep in mind, because you could also choose coordinates that are just expanding, and by that you can kind of create a surface where the information flow is kind of only outflow, but you don't want to discard your numerical domain. So you could create something like this also outside of the apparent horizon, but you are interested about the physics near the apparent horizon also. So you don't.
Yes, I don't understand why one focuses on the apparent horizon, but yes, that's probably my problem. But anyway, yes.
Okay. And then I want to come more to this expansion. So in spherical symmetry, you can write your spatial line element like this. And then the expansion is just given by this formula here, where K is extrinsic curvature. And you can also write this in this form, so time derivative plus coordinate light speed, spatial derivative, and then you have this factor here. And you see gamma is this factor here. It could behave however it wants to behave. And however, if you now make this choice that your radial coordinate is given like this, so it's an areal radius, then these equations simplify to a form like this, where the expansion is proportional to your coordinate light speed times the radius. And that means whenever the coordinate light speed is 0, also your expansion is 0. And now in these coordinates, that means your outflow, or this crossing, the 0 crossing of the coordinate light speed, is exactly at the position of the apparent horizon. And in this way, it cannot happen that inside the apparent horizon, your coordinate light speed is suddenly positive and you get data coming into your numerical domain. These coordinates also have the nice property that the position of the apparent horizon can only grow because the apparent horizon area can only grow. And this coordinate also only the radius, the radial coordinate can grow. Okay, Istvan Raj has a question, I think.
Istvan?
Yes, I have a problem with this argument. If you have the area radial coordinate, then in the three-dimensional metric, your lapse is going to be unbounded at the apparent horizon. So you cannot use the area radial coordinates if you wish to, describe your geometry up to the excision surface. I miss something, but as far as I know, the lapse is not going to behave nicely for you.
No, so actually, in this approach, the lapse will be the same in the uppercase foliation and in the lowercase, or in the uppercase coordinates and the lowercase coordinates. The lapse actually doesn't even change.
Okay, please check it. Yeah.
Mm-hmm. Okay. So, and as I said, so we have seen I changed the radial coordinate, but changing the radial coordinate doesn't change your time coordinate. So in this application here, we didn't even go to a different foliation, but the foliation is the same. Okay. Oh, and here I also have some image. So we made an experiment where we have a scalar field, around the black hole. The scalar field comes into the black hole and is swallowed up. And on the left-hand side, so that is shown on the right-hand side here. On the left-hand side, I show you the coordinate light speed. And you see without this approach, the coordinate light speed becomes positive for a short time. It recovers, but still it becomes positive. Whereas with our new approach, the boundary remains outflow all the time. Okay. And now I also want to talk about an application where we actually go to a different foliation, where we also change the time coordinate. So what we want is we want to control the coordinate light speed of basically in the direction outgoing of the numerical domain, so into the black hole. And for that, one has to choose coordinates like that, where V is a null coordinate, so it satisfies the iconal equation. And because you don't know the metric in advance, you can't write down the Jacobian transformation for this analytically, but you can co-evolve your Jacobian that you need to write down the dual foliation equations. And you can do this by, in fact, co-evolving these metric derivative components of this null coordinate. And yeah, why would one want that? So the application we have in mind is to control the infalling matter. If now this coordinate light speed would be very different from -1, then you could have redshift or blue shift of your infalling waves, and then you can get a pileup of wave oscillations that is difficult to handle in numerical relativity. And here on the right, we show then the difference in the for the uppercase coordinate light speed and the lowercase coordinate light speed. And you see in the lowercase case, it just remains, it stays at 1, except near the outer boundary where we have some transition region, so that in the outermost region, both coordinate light speeds are identical. So, and with this, I want to end. And if there are any questions left, I'm happy to answer them.
Okay, thank you very much. Clapping for everyone. Thank you for your presentation. Yeah, any questions? There were some questions, but I think we have some few minutes. We take out some minutes from the break. Piotr, how do I unmute you? Piotr? Yeah? Us to unmute? No. How do I give a... Yeah, Piotr, can you? Yeah.
I have a question. Well, I guess everything you showed is in spherical symmetry. Is there a chance that this implementation of excision will work in general without spherical symmetry?
So yeah, we think that it will be possible. So in principle, it's not much different. It's just more complicated. So it should be possible in principle. And that's, of course, the plan for the future.
Thank you.
Can you expand on this, something you said before, namely that this Jacobian is something you specify by hand? So it's not something that is evolved by the equations to get good properties or something like that. It's just you put it by hand and that's it.
Well, so you see, you specify this coordinate transformation. And this coordinate transformation leads to some Jacobian. And you need this Jacobian.
Initially, you mean, or later, or what? Where do you specify this? This is a global choice? This is an initial choice? Or?
Yeah, so this coordinate transformation is valid.
For example, right?
Yeah,
V
so R is your radial.
V should be null in the real metric. Okay.
Exactly.
Okay.
Yeah, so
R is the usual kind of square root. Okay. Yeah.
Exactly. And in this case, we can't write down the Jacobian explicitly, but we can write down evolution equations for the Jacobian that we then co-evolve this metric equations.
So this gives you some kind of domain of dependence surfaces.
Yeah.
Thanks.
If I may, just a quick question. So you started with motivating your this method by starting with gauge choices. So which gauge choices? What gauge are you using? Are you using punctures or?
No, it's not puncture. So we now have two gauge choices, right? We have one for the tensor basis.
Yeah.
For the tensor basis, we just use whatever is good. So usually something like damped harmonic gauge that is used by SPEC or BAMS or Spectra. And then we have this gauge choice for our working coordinates. And that is basically free to specify. So here I can't tell you what is lapse and shift in these equations. Because here we were interested to make the gauge such that the coordinate light speed is.
Oh, I see.
Okay. But you can also choose that, for example, the shift is exactly 0 in your lowercase foliation. And that's actually also an application we discuss in this paper, but I haven't put this in the talk here.
Okay, thanks.
So I have a question. This approach where you have these tensor bases and coordinate, I'm not sure. I certainly don't understand the role of the tensor bases, but I want to ask. I mean, how does this differ from if you use generalized harmonic coordinates with a background metric of your choice, and you look at gauge source functions, which are defined in terms of the difference of the Christophels and so on. I mean, then you can add whatever damping you want, and that approach does not specify any coordinates at all. I mean, you're still free to choose coordinates as you like. I mean, is that sort of what's going on here? I mean, that tells you what reduced field equations to use, but it does not fix the coordinates.
Yeah, it could be that there is a relationship. So I wonder, in this approach that you mentioned, the background metric, do you have to know that background metric in advance?
Well, I guess you have to invent a background metric, and you might change that from time to time, so to speak. But I mean, this I would expect that there is something, such an approach could be viewed from this point of view, where you have this dual coordinate formulation.
So it could be that there's some equivalence. After all, we have our Jacobians at every time. So we could always just transform our metric from one tensor basis into the other if we wanted. Yeah, but probably there is a relation, but I don't know whether there are some shortcomings or not. I haven't thought about that.
Okay.
Well, I have another question. There are all these new nice theorems by Dafermus and Luke using double null foliations, which were both at the basis of the Christodoul-Kleinerman work, and then they seem to be very useful for proving things about GR. Has anyone been trying to code the double GR in double null coordinates and see if one gets something workable out of it?
So I think, I mean, not with this thing. There has been, for example, a study of scalar field collapse in spherical symmetry using double null coordinates. And one could also do double null coordinates in this approach. I think
that's something actually which came to mind too.
I think that was even discussed in this paper here by Hilditch in 2015 already. that dual foliation could be a way to implement this. But yeah, it hasn't been implemented yet.
Because your V surfaces just give you one part of the domain of dependence. The U would be the other one. So this would make clearer where the information stays and propagates and so forth.
Yeah, exactly.
John? Can you hear me?
Yes, Helmut, yeah.
I'm doing this noise. I don't know what it is. John Stewart coded double null coordinates with the conformity declaration. So it has been used in various contexts.
Okay.
Any further questions or comments? I don't see any. So let's thank all the speakers of this morning session. Again, thank you very much. And I think it's time for a coffee, right?
And let me just tell my colleagues, co-organizers, that we actually have 10 minutes left. Maybe we could meet in another room to discuss the organization of things for maybe the next meeting. Lars, I sent you a chat message.
Oh, okay.
So if Piotr, Helmut, somebody could open another Zoom session, because if I try to open one, then I'm going to bomb this one out. And send an email. Can we do it now? We have 10 minutes. That should be okay.
How do we do this? I have no idea.
Just to discuss the next meeting.
I understand your intention, but how do I technically go to another room?
So Lars, well, somebody has to open another Zoom invitation to in an email.
Okay,
and we could.
I'll try to do this. Let's see here.
So check your email and we connect to the session opened by Lars.
Yeah, but I have to close this. I have to leave this meeting.
Yeah, and since you're the host for you're the speaker for the next one, that might be actually the chairman.
Yeah.
Okay.
So when do we start, by the way?
Okay, good. So maybe I have to take back my idea to do it now, and we do it after the last talk then.
Yeah. So, but are we starting now at?
Well, we're starting in 10 minutes.
Okay.
Okay. So Lars, or Maciek, someone can open a new Zoom session at the end. An invitation to everyone.
Yes,
in the committee to join and.
Sure.
Okay. Good. So see you in 10 minutes.
Thomas, I do have a question about these recordings. Thomas, can you hear me? Thomas, he's gone. Okay. Oh, I'm still here. Okay, so if someone can hear me, then I'll remind you that there is this Garden Town where you can go and chat with other people. So if you don't want to use, we don't have to use Zoom all the time. So if you want to just hang out and say hi to your colleagues, ask speakers questions, then there is this Garden Town. You should have received an email from me with a link and a password. Yeah, so please, if you have your own coffee, then go there and meet and chat. I will try to do this as well.
Maciej, you're live, right? With your microphone. Do we have all the speakers now for the last session?
Yes, they're all online and
Okay. Great.
So Thomas, will you take care of making the speakers co-host or whatever they have to be?
Exactly, that's what I'm doing.
Okay,
yes.
great.
All you have to do is the moderation.
Yeah.
So Thomas, and somehow this, do you know if I start new recording, my previous recordings will be overwritten or what?
No, that
No, okay.
it will append everything to this one file it created, so it will be larger. And
I see. Okay.
And afterwards, when you convert to MP4, it will separate this into two different recordings.
Okay, I see. Okay. Thanks.
Sure.
So I'm
Okay. So yeah, I guess we can start if everyone has come back from the break. Okay, so we have now the last session of this conference, and the first speaker is Eric Buck from sorry for the pronunciation, from Warsaw. We'll talk about axisymmetric isolated horizons in the presence of a cosmological constant. Okay.
Thank you. Can you hear me?
Yes.
I would like to thank the organizers for having me here. This is from the joint work with my supervisor, Professor Lewandowski. I will start with reviewing some definition from so-called quasi-local approach to black hole horizons. Then I will present general form of metric on axisymmetric extremal isolated horizon, and then I will embed it in Kerr de Sitter spacetime. Yes. So the whole idea in this quasi-local approach is to relax definition of Killing horizon, but to keeping them strong enough to still have some tensors and equations to work with. It can be used to describe this isolated black holes or black holes in some sort of equilibrium. It can be developed in arbitrary number of dimensions, but I will restrict myself to usual 4-dimensional spacetime with cosmological constant and vacuum. Now, first thing, first definition is non-expanding horizon. It will be smooth null hypersurface generated by some null vector L. Well, this horizon is congruent, so we can define optical scalars on it, and in particular expansion, which will equal to 0. It will, of course, mean that area of our horizon stays constant. We'll assume that horizon is topological product of some closed topological manifold and real line. Again, I will restrict myself to the sphere. So this delta in equation to this sphere. We assume that L satisfies dominant energy conditions and that Einstein equations are satisfied on horizon. Such a horizon can still be too dynamical for our uses, so we can restrict it further. namely, well, you have this heuristic picture here. We can assume that geometry of our horizon stays constant, stays the same in time, or mathematically speaking, we will assume that Lie derivative along L in equation, you can see it in equation 4. This Lie derivative and covariant derivative induced from space-time on horizon commute while acting on any vector tangent to horizon. Now, on such isolated horizon, I can define important quantity, rotation 1 form. You can see the definition in 5. It's connected to angular momentum of black hole, and in particular, if this one form vanishes, then black hole is non-rotating. By contracting this rotation 1 form with L, I get kappa L in equation 6. It is surface gravity. It's proportional to temperature in black hole thermodynamics, and if it vanishes, then isolated horizon is called extremal or degenerate. Now, with all that, if I take my delta, my sphere, which is some transversal section of horizon, then vacuum Einstein equation induce constraints in equation 7 on this section. Capital indices pertain to this section delta, and these equations are called near horizon geometry equations. That's the equations we can solve searching for metric.
So a question. I
yes.
thought that this equation is holds when the in extremal case. So you're assuming extremal now, or is this equation true in general?
I assume extremal.
Oh, okay.
Now you can show, you can just integrate equation 7. We have constraint 8, namely cosmological constant must be less than Gaussian curvature of our section. Yes. So I wanted to concentrate on axisymmetric horizon. So I can introduce familiar coordinates theta and phi, where this rotational symmetry is generated by derivative over phi. And now metric on my section has the general form in equation 9. Furthermore, I can introduce coordinate x in equation 10. Capital R is pseudo-radius of our horizon. It's connected to area, as you can see in equation 10. So now metric has the form given in 11. It's still metric on section, of course, and it is given pretty much by this function p squared. Now this function must admit certain limits given in 12. These describe this function on poles, and well, we want our metric to be regular. Otherwise, you would get these cusps you can see in this another heuristic picture. We don't want that, so we have these limits. Now, to simplify calculations further, we can Hodge decompose rotation 1 form in equation 13 into potentials u and b. They are only function of x because of rotational symmetry. And then we can put all of this into near horizon geometry equations and solve them. And we get two classes of solutions. First class is for lambda r squared equal to 1 or to cosmological constant equal to Gaussian curvature. Function p is simply 1 minus x squared, and potentials vanish, potentials u and b. So rotation one form is equal to 0, so horizon is non-rotating. When you can calculate metric q, and well, it turns out it's just your usual metric of sphere in equation 17. The other class of solutions is for lambda r squared less than 1. You can find function p in equation 18.
And question?
Yes.
I always thought that lambda can be scaled away, right, or something like that, so normalized. So I'm just curious how this. Can you comment on how this arises here? This kind of why is one special or something like that? I thought that only the sign would matter, and that's wrong.
Well, this is special because that's the only case when omega would vanish, I would say. But that's what I get from solving equations.
Mm-hmm. Okay, thanks. I was obviously confused about the.
No, but if I may comment, so when we there are sort of trivial scalings of this equation. It means very easy when we scale metric tensor by constant.
Exactly. Right,
if lambda were 0, then this is just a symmetry of equation. If lambda is not 0, then lambda is also rescaled. But scaling free parameter is lambda times r squared. So this parameter is constant upon rescalings.
Even if you scale this, then you can rescale the metric back or something like that. Yeah. Okay.
Yes, so that's why we introduce this parameter lambda times r squared, and effectively this, you can see everything depends only on this parameter.
Okay, great, thanks. Sounds like something to do with Naria or something like that, right? Maybe.
Yes, R is a coordinate area. So 4 pi times r squared is not coordinate, it's area coordinates. So 4 pi times r squared is the total area of this horizon.
Yeah, thanks.
Yes, so we have this function p. Parameters are constrained as in 19. Well, you can calculate the potentials u and b given in 20. Yes, b0 and u0 are some constants, and capital omega is defined in 21. So these are general solutions. Now I wanted to embed it in Kerr de Sitter spacetime, or anti-de Sitter, because we don't really make it doesn't really matter if cosmological constant is positive or negative. So you can see in 22 Kerr anti-de Sitter metric. Well, the important part in 23 is that horizon in this spacetime coincides with such R that polynomial delta R here at the bottom of 23 vanishes. Yes. So we can make this vanish, and we can compare parametrization in this metric with our parametrization. And we get equations 24. R0 is some root of delta R. Now we want our horizon extremal, which corresponds to delta R, which corresponds to R0 being multiple root of delta R. So we calculate the determinant of delta R, make it vanish, and we can translate one parametrization into other. In 25, you can see square of angular momentum of anti-de Sitter black hole and its mass, given by lambda r squared. Yes, now function p, even in 26, you can see it has the very same form as the one I've calculated earlier, which is great. Parameters are constrained in the same way, where lambda r squared equal to 1 recovers 1 minus x squared. As I said, these results agree with earlier ones.
Question. So,
yes.
but so when you're saying an embedding, in fact, you're finding a killing horizon in Kerr anti-de Sitter, which gives the right geometry. That's or you're just getting another hypersurface.
That's I'm finding killing horizon.
So you're finding a killing horizon. Thanks.
Yes, well, that is the condition, like delta r equal to 0, right? And the double root.
Yes, of course, yes.
I've also calculated triple root of delta r, which should be some very special place, but I don't see like nothing particularly interesting, to be honest. You have it in 28. Lambda r squared equal 3 minus square root of 3 by 2, and value of this root are 0. Yes, and that is all. Thank you for your attention.
Okay, thanks. We have time for a couple of questions. So, I mean, I've heard about these extreme horizons several times, but so could you summarize sort of conceptually what is the problem that you have solved in this talk?
I have this extreme isolated horizon, right? And there are constraints here in equation 7, right? These are just constraints coming from Einstein equations. And I've solved them in this axisymmetric case with cosmological constant. I have found the metric, right? So this Q in 11, this Q, and this P given by, here, equation 18 or 15. So I solved this equation in this axisymmetric case. And
so
then
you have uniqueness actually in that.
Uniqueness.
Yes, there is the uniqueness in the sense that there are only the Kerr de Sitter and de Sitter solutions.
Right. And this, I understand this is a conjecture that, or it's sort of believed that this would hold in more generality, or what? I mean, for example, if you relax axisymmetry.
Well, that's in the lambda equals 0 case. That's the well-known old problem, right?
Right.
Exactly. But and of course, in the other case, lambda, it's also an interesting problem. But given that there's no theory of uniqueness anyway, then it's not as important gap as different one. But maybe I can ask another question. So. When lambda is 0, then this is the famous theorem of Lewandowski and Pawłowski or Hajicek, that all these solutions are the Kerr ones. And so this is a generalization of the theorem to other lambdas, if I understand it correctly.
Yes.
Now, my question is, there was some work by Nurowski and Randall about this. So they were looking at axisymmetric solution of this kind of the system equation. So is this result included already in their analysis or not? I don't remember offhand, but they were looking at a quite general class of equations in this the form you wrote.
This I do not know. I don't recall that paper in particular. So I'm sorry.
Jurek, would you know whether this is?
Well, yes, well, I checked their paper, but there were some very implicit conditions in this paper derived, and I couldn't conclude anything specific.
So it wasn't clear. Okay.
From that.
And they certainly didn't show an embedding, right? So the bottom line here is that it's really coming from the Kerr family, right?
Right.
Which is a nice result. Yeah.
Okay, so we should move on to the next speaker. So thanks for the nice talk.
There is still one question in the audience.
Okay.
Perhaps you have time. Ivan, you have the rights to unmute.
Yes. We should, if you can speak. So David.
Hello.
Hello.
Do you hear me now?
Yeah, we can.
Yeah.
Okay, because I asked the question, but you didn't hear me. So I would like to ask a question. Why do you only consider a situation when you have regular sphere, namely that the deficit angles are 0?
As opposed to what?
Because in the recent work that I done with Professor Podolsky, we considered more general situation when the deficit angles were non-zero. So I am interested in your particular case. Did you?
Yes.
What is your motivation?
So probably, yeah. So you can also do this. You can also relax this assumption. We just wanted to usually when you consider some differential equation on a manifold, then you assume that solutions are regular everywhere. But of course, if you assume some points, allow points in which solution is not regular, then you can obtain more solutions. And also, it is possible that in space-time there exists, probably if you consider even simple case of de Sitter space-time, and there is a huge symmetry. So this killing horizon is a killing horizon for many different killing vectors, and in particular, the killing horizon is also extremal killing horizon. And indeed, I think in that case, this killing vector, which makes it extremal killing horizon, vanishes in some points. So when the killing vector vanishes, then there may be some irregularities for the structures it defines. So yes, I agree that it's not completely irrelevant to consider also to relax this assumption.
But you could also think about torus or higher genus topologies, right? So with lambda negative, that's still compatible with the equations. And something I said in the middle that this limiting value sounded like Nari I meant, and I'm astonished that Nari doesn't show up. But maybe I'm wrong now that Nari has no. Can you have degenerate horizons in a Nari matrix? I mean, I would expect if you can, then certainly they should show up here. So
I'm not sure what kind of horizons are there, but it may be that horizon. So different spacetimes can admit define a same solution to extremal horizon equation. So this metric tensor and omega may be the same for different spacetimes.
Right. So maybe you can have both an embedding in Kerr and in Nari because it's
there may be
it's a
more
very
embeddings.
right.
Yes.
Yeah. Okay.
Okay, good. So I guess we should move on to the next speaker.
So I will stop sharing.
Okay. Okay. So our next speaker is Parth Bamania from ICC, and he will speak about precession of relativistic orbits of a particle in black hole and naked singularity spacetimes. So please.
Hello, can you hear me?
Yes.
Yeah. So, okay, thanks. First, I would like to thank the organizers for giving me an opportunity to present my work here. In this presentation, I'm going to talk about the precision of relativistic orbits of a particle in the black hole and naked singularity spacetime.
So can you, sorry, can you speak up a little bit?
Okay. So these are my collaborators, and my talk would be based on this work. If you are interested, then you can refer it. See, the outline of the talk are given here. And to begin with the introduction, I will talk about the possible causal structure or space-time geometry to describe the galactic center and its dynamics. Then I will discuss the derivation of the general orbit equation for the spherically symmetric and static spacetime. And using this orbit equation, I will show the periastron precision in the Schwarzschild black hole and Joshi, Malafarina, and Narayan naked singularity spacetime, and then discuss about the nature of the periastron precision in the Kerr and deformed Kerr geometries. And at last, I will conclude with the important result of our recent work. So, as we know, the Newtonian mechanics failed to explain accurately the perihelion precision of Mercury. And to explain this phenomena, we need to consider the general theory of relativity. And by the observation, Mercury moves its perihelion forward by 43 arc second per century, and it is very small compared to the precision of stars uh, near the galactic center of the Milky Way. So you can see the recent observation such as the Event Horizon Telescope, Gravity, Symphony, and UCLA Galactic Center group have been focusing increasingly on the investigating the nature of the galactic center. And there are many S stars which are rotating around our galactic center, and some of them are very close to the central massive object. Therefore, their orbital precision will tell us about the nature of the space-time and causal structure around of the Sagittarius A star. So, as you can see in this figure, S62 is known as the shortest period star. It's around the 9.9 year orbital period, and it is very close to the galactic center. And the astrometric data of the A stars are given in the declination and right ascension. And for more detail, you can refer these papers. So the existence and observation of the shadow is not sufficient.
So question, can you
Yes.
go back to your slide? So SO102 also has gone through the whole period now?
Okay.
The orange one, SO102. It's what is the period of SO102?
SO102 is a period of 11.5 or something.
So the both, I mean, I knew about S2, but so the red and orange ones have full periods now. Okay.
Yeah. The SO102 is also known as the S55, or its orbital period is around 11.5 years. So the recent observation by this paper gives the another shortest known period star, and that is the S62.
Yeah. Thank you very much. Thanks.
Yeah. So the as we know, in April 2019, the Event Horizon Telescope revealed the shadow image of the galactic center of M87, and in near future, it is going to be reveal the shadow image of Milky Way galactic center, and there exists the compact radius of Sagittarius A star, and the existence and the observation of a shadow is not sufficient or need not ensure the existence of an event horizon necessarily in the galactic center. So we need a further and more detailed theoretical as well as observational analysis in order to decide whether the galactic central object is a black hole or a other exotic compact object such as the naked singularity or Grey star. So, from the nature of the orbits, one can predict the causal structure of the space-time at the galactic center. So, in general, the outside a massive body, one can consider a vacuum as pressure and density drop almost to zero. And therefore, outside a massive body, we generally consider the Schwarzschild spacetime as an external spacetime, and inside the this massive body, it can't be a Schwarzschild spacetime as pressure and density are not zero inside. So it is a well-known the solution of Einstein equation for the it is a spherical, symmetric, and homogeneous dust collapse, and it is always terminates into the Schwarzschild black hole, and the metric of the Schwarzschild black hole described by this equation, and where the 2m is the Schwarzschild radius, and the d omega square is the metric of two sphere. So as we know, due to the flat velocity profile of stars in galaxy, we consider an unknown spherically symmetric matter distribution throughout the whole galaxy, and this matter called as a dark matter, or you can consider other matters and others baryonic matter. So it is considered that the galaxy reside inside a dark matter halo, and therefore outside the dark matter halo, one can consider the Schwarzschild space-time. So, however, inside the dark matter halo, density and pressure is not zero. So, therefore, one needs to consider more physically realistic space-time, and that is seeded by dark matter or other baryonic matter, and it is a well-known picture describe the rotation curve of spiral galaxy M33. So now I am going to talk about the one of the solution of the gravitational collapse, and it is the equilibrium state of the gravitational collapse, and the it is known as the Joshi-Malla-Farina-Narayan naked singularity, and it is formed from the gravitational collapse of matter cloud with zero radial pressure and non-zero tangential pressure. So and it is also obtained via the dynamical evolution of a matter cloud, starting with some regular initial data. So the space-time geometry of Joshi-Malla-Farina-Narayan naked singularity described by this equation, and it is a spherically symmetric and static space-time where the m naught and rb are the positive constant, and in physical sense the rb is the radius of the distributed matter halo. So now from the general spherically symmetric and static space-time, one can derive the orbit equation using the time lag geodesic and some conservation laws of energy and angular momentum. So one can derive the orbit equation for the general spherically symmetric and static space-time, which is the second order nonlinear differential equation, and where GTT, GRR, and G55 is a function of R, and 1 over R is equal, we consider the 1 over R is equal to U here. And the function of A of U and B of U and C of U described by these equations. And in this equation, where gamma is the conserved energy per unit rest mass, and the H is the conserved angular momentum per unit rest mass. And all the throughout the whole calculation, we consider the orbital precision in the equatorial plane. So that's why we consider the theta equal to pi/2. Now, to understand the nature of the orbital precision in the spherically symmetric and static spacetime, I have considered here the Schwarzschild black hole and Joshimala Farina Narayan one naked singularity model as a background spacetime. And you can see here in figure A, it is described the particle orbits in the Schwarzschild black hole, where the dark region shows the position of the black hole, and a brown circle shows the minimum approach of the particle towards the center, and it is called the periastron points or position. So, and in the figure B and C, represent the particle orbits in the J-main naked singularity, and you can see an interesting behavior that emerged is the orbits around the naked singularity allows the negative or opposite precision as compared to the Schwarzschild black hole. Here I mean to say the negative precision is the phenomena in which the angular distance traveled by a particle in between two successive perihelion points will be less than 2 pi. So here in figure A and B, you can see the angular distance traveled by a particle in between two successive perihelion points is greater than 2 pi. So it is known as the positive precision, and it will be shift into the direction of the particle orbit. So here in figure C, it is less than 2 pi. So therefore it is called the negative precision. In other words, if particles orbit will precede or shift in the direction of the particle orbiting direction, then it is known as the positive precision. While for the if particles orbit will precede in the opposite direction of the particles orbiting direction, then it is known as the negative precision. So as you can see, the orbital shift for the positive and negative precision. And the if we consider a more physically realistic compact object at the galactic center, then we must consider the rotating compact object. And if we derive orbit equation using the time lag geodesy for the curved spacetime and plot the numerically, we get the periastron precision in the Kerr space-time. And as you can see, the in this figure, it shows the orbits of a test particle in the Kerr space-time, where this red solid lines indicate the particles orbits in the Kerr, Kerr and extreme Kerr black hole, respectively. It depends on the value of the spin parameter. If I consider this spin parameter equal to 1, then it is known as the extreme Kerr black hole. And blue lines considered for the Kerr naked singularity, where the spin parameter exceeds the value of that mass parameters. And here the plots are given for the prograde and retrograde motion of the body. So for that, I consider the spin parameter value in the positive and negative sense. So next, now, as we know, it is very much difficult to solve the second order nonlinear differential orbit equation analytically. And so by considering the first order eccentricity approximation, one can consider the solution of the differential equation as given here, and where the P and M are real positive constant, and that are used to determine the nature of the orbit's precision. And if the value of the small n is less than 1, then the positive precision occurs, and while for the m, the value of the m is greater than 1, we will get the negative precision. So you can see here in this figure, here one can see the negative precision is not possible in the curved spacetime, as it is not it is not exceed the value of small m greater than 1. Now, if we introduce some parametric deformation due to the electromagnetic radiation by accreting matter around the rotating black hole, then it gives the deformed curve metric, and it is written here as uh, by this metric, and where the rho square and the deformation given by this two equation, where the epsilon is the deformation parameter, and so the curved spacetime has the oblate shape, but however the deformed curved spacetime is more oblate for the deformation parameter is less than 0, and more prolate for the deformation parameter greater than 0. So in this paper, it is stated that the deformation parameter is unconstrained, and however in the other papers, the author discussed the possible maximum value of the deformation parameter is the less than or equal to 19, and that value define some Faraday rotation polarization experiment, and so here we are consider the value of the deformation parameter up to the this range, and one can derive the position of the inner and outer horizon of the deformed curved spacetime by solving this equation. And here in figures, you can see the shape and position of the event horizon. Uh, horizon in deformed curved spacetime for various value of the deformation parameter and spin parameter. So it can be seen that for the value of the deformation parameter equal to 1, and spin parameter equal to 0.8, there exists some directional naked singularity around the equatorial plane, and this uh, uh, directional naked singularity you can see in the 3D view here, and now now from in this figure, the shaded region shows the existence of naked singularity in deformed curved spacetime, and the area above the blue dashed line in the shaded region is the region where the negative precision is possible, and where the red dots are the solution points for the negative precision, and the remaining unshaded region shows the existence of the deformed curved black hole. And you can also see from this image the deformed curve space time gives the negative precision for the value of the up to the 19 range, and this gives you the negative precision region. And the conclusion of my talk is the observation can give us the essential information about the causal structure of the galactic center and its dynamics. And the interesting difference from our result is that in naked singularity spacetimes, the particle bound orbit can precede in the opposite direction of the particle motion, which is not possible in the black hole spacetime. And the stars can have the negative precision if the naked singularity exists at the center of our galaxy. On the other hand, if stars show the positive precision, then black hole or naked singularity spacetime can describe the spacetime geometry. Thank you for listening, and if you have any question, you can ask.
Okay, thanks. So questions?
So maybe I will have a question.
Yes,
S2 is supposed to have a orbit precession compatible with Schwarzschild, right? That was a recent paper. Now, of course, it's the numbers are. Yeah, I think it's very early to be able to make solid claims like that. And how is it compatible with Sagittarius A star being Kerr, for example? So do we, if it was not Schwarzschild by Kerr, would this how much would this precession change? Has anyone looked at that or?
The data of the S2 star is up to the 2019 or 20. Recently, the Gravity Collaboration actually published a paper on the Schwarzschild precision, but they take the higher order approximation for the Schwarzschild model, and Schwarzschild black hole always gives the positive precision, and the second orbits of that S2 star also gives the plus or minus error, and that would be also consider in the negative or positive precision. So I mean to say that the data available of the S2 star is not sufficient to distinguish how the next orbit will precede in which direction the next orbit will precede. So it is up in the plus or minus error.
So
well, I thought, yeah, go ahead, Lars.
I just wanted to ask, I mean, what is known about the spin of the central object, this Sagittarius A star? Does when this Einstein telescope data or this horizon observation, when that comes around, will that also give some estimate of the rotation?
Pardon me, I can't understand.
Well, I mean, so it's certainly not a Schwarzschild at Sagittarius A star. If it's a black hole, it's certainly a rotating black hole. But what's the A parameter of that, or what's the angular momentum per mass of that object? Is that known? And will this horizon observation, is it called Einstein telescope, will that give information about the angular momentum per unit mass?
Yes, probably the observation will give the rotation parameter. The existence of the Sagittarius A star at the galactic center, it's of course there must be some rotation. It is not a static, but the slowly rotating object will differ some orbits, and that will that's why I consider the Kerr black hole and deformed Kerr black hole. These are the possibility and the prediction of the orbits, and there are many A star actually. So the if some star can precede in the opposite direction or in the negative direction, then the black hole can not explain this phenomena. So there are the possibility of other orbits at the galactic center.
Okay, so if there are no further questions, so let's thank Parth for this very interesting talk.
Thank you.
Yeah. Okay, so the next speaker is Tobias Sutter.
Hello.
Hello. So you can share your screen.
Yes, and 1 second. Okay, so now I hope you can see my screen.
Yeah.
And I have the black bar on the sides for your camera. Yeah.
Okay, so Tobias will speak about vortical null geodesics in Kerr.
Okay.
Please.
So thank you for, first of all, to give me the opportunity to present my work here, which I've conducted in the course of my master thesis, which is supervised by Maciej Maliborski and Piotr Kruszczyl. And to start off, let me give you a brief motivation. So as we already heard in the previous talk, Kerr spacetime describes a rotating black hole and is therefore often used to simulate and visualize the shadow of a black hole in the exterior region, so somewhere outside of the horizons. And we want to do something similar, but except that we want to study null geodesics in the extended Kerr spacetime, so not necessarily outside of the horizons. And with this, we want to visualize new features. So let me quickly go through a few basics of Kerr spacetime for those of you who are not completely familiar with it. So this is the metric in Boyer-Lindquist coordinates, where you have the mass parameter m and the rotation parameter a. And you can see that the metric has problems at sigma and at delta being 0. So this sigma being 0 actually corresponds to a singular ring lying in the equatorial plane, which is a curvature singularity, whereas this delta being 0 corresponds to the two horizons. And I already want to mention here that there are two asymptotically flat regions of this spacetime, namely one for positive radii and one for negative radii. And you can travel between those two by crossing the disk spanned by this ring singularity. So for example, you can start at positive radii, cross the two horizons, and then cross this disk. And then you're in a completely other space-time region where actually you don't have any horizons because this delta has no zeros there. So you can move freely, kind of. And then only by crossing this disk once more, you come back to your original region in space-time. Two other coordinate systems which are rather helpful are these Eddington-Finkelstein-like coordinates, which are similar to the Schwarzschild case in the sense that they cancel the singularity at the horizons, and therefore we will use those to solve the geodesic equations of motion. So our geodesics can actually cross the horizons. And furthermore, there are these Kerr-Schild coordinates, which we will use for visualization because they have this nice property of this underlying flat space-time metric. Right, so to give you a feeling of the global structure of Kerr, this is a projection diagram already introduced by Rafaela yesterday. So here you have one asymptotically flat region at positive infinity. Then you can go inwards across the outer horizon and the inner horizon. And somewhere in here is this singular ring, which you need to cross to reach this other asymptotically flat region at negative infinity. And here's a good point to mention what we want to do. Namely, we want to put an observer at negative infinity, so far away from the black hole in this negative region, and put the light source somewhere outside the horizon, and basically answer the question, how would this observer at negative infinity perceive this light source? So the task is to find a null geodesic, which starts at the source somewhere outside of the horizon, crosses both horizons, goes through this disk, and then finally escapes to negative infinity to be able to be perceived by the observer. So quick introduction into Kerr spacetime, the geodesics. So there are 4 quantities which are preserved along any geodesic, which is this mu squared. Then its energy, the angular momentum in the azimuthal direction. And this 4th one is the so-called Carter constant. In our case, we want to study null geodesics, which have, of course, mu squared being 0. And in this case, only these two ratios are actually independent. And so we can formulate and express the equations of motion in these quantities, in this lambda and this eta, instead of L, Q, and E. And I want to mention here that I'm not going to talk about each geodesic equation of motion in detail and explain how to solve them, because this is not important for understanding the results I want to show. And it's only basically detail. But there is one equation of motion I want to mention in more detail, which is the radial equation, because this basically determines the global behavior of our geodesic. So on the left-hand side, you can see this derivative is with respect to tau, which is so-called Mino time, and which allows us to decouple the equations of motion. And on the right-hand side, you can see this new r is only the sign choice of this square root. And the radicand here is the so-called radial potential, which of course needs to be positive, otherwise you get a complex path, which is not physical. And to analyze this potential, you can do the following, namely you can specify this A and M and also this eta, and then plot this radicand only in this lambda r plane, where you will find the following, that there are these gray regions where the radial potential is negative. So these gray regions are the forbidden regions, and the white regions are the allowed regions where all motion must take place.
Sorry, could you remind what's the meaning of this, the eta and lambda again?
So basically these are the angular momentum of the geodesic, as well as this fourth constant of motion, the Carter constant.
Okay, so those are those dimensionless quantities. Okay.
Yes. Yeah. But I will relate them later to a more helpful understanding in actually on the next slide. But just quickly, these lambda are plots. So again, the motion takes place in the white regions, and this lambda, as it is a constant of motion, stays constant, whereas this r can change. So any geodesic can only move on horizontal lines in these plots. And when hitting one of these forbidden regions, it necessarily needs to get reflected. And our scenario is now this, that our observer should be at large negative radii, so somewhere over here, and the source should be somewhere out here. And the task is now to connect those 2 points by a horizontal line, which is impossible for positive eta, and also for eta being 0. But only for negative eta, there is this gap opening up. So this is actually called the inner throat, whereas this large gap out here is called the outer throat. And only in this parameter region or constant of motion region, you're able to actually connect the source to the observer. And we could now do the following to analyze this potential further in this lambda eta space. But again, I mean, this is rather abstract. So for visualization, it's often more helpful to define these impact parameters, which due to time reasons, I'm not explaining in great detail, other than by projecting the angular momentum in the azimuthal direction, as well as the angular momentum in the polar direction. By projecting these angular momenta on the sky of an observer very far away from the black hole, one is able to define a kind of a coordinate grid on the sky of this observer when they look directly at the center of symmetry. So this is actually a coordinate system on the sky of the observer. And in this coordinate system, this alpha is the displacement perpendicular to the axis of symmetry, and this beta is the displacement parallel to it. And so you can think of this basically as what an observer would see when looking directly at the black hole. And this way we get rid of these abstract constants of motion and relate them to kind of a visualization. And now we can actually study these openings, these throats from the plots before in this new
Tobias, question.
Yes?
So this theta 0 is the angle of the source, is it, or?
No, actually it's the polar angle of the observer.
Okay,
Sorry,
thanks.
I should have mentioned it. So the drawback with these impact parameters is that we need to specify the position of the observer here. But we gain the visualization. So we can now discuss these throats in this new impact parameters, where these are the conditions which define these openings. And in the Schwarzschild case, you only have the outer throat, which corresponds to the black hole shadow as seen from the exterior region. For higher rotations, this gets deformed and moves to the right. And also for a rotating black hole, you have this inner throat opening up, which are exactly those geodesics which we are interested in, because those are the ones which can start at the source at positive radii and reach our observer at negative infinity. Right. And before showing any visualizations, a few words about the solutions to the geodesic equations of motion. So actually last year, Gralla and Lubsaska solved the integral equations of motion using elliptic integrals and elliptic functions, but they used Boyer-Lindquist coordinates because they were only interested in the Kerr exterior, whereas we use Eddington-Finkelstein-like coordinates. And alternatively, we can also numerically solve the equations using the second order equations. But either way, what we get is that we need to specify the black hole's parameters as well as the space-time location of our observer and the radial position of the source. And then for each point alpha beta inside this small inner throat, we can calculate the remaining space-time location of the source. And in this talk, we're only basically concerned with these angles, psi s and theta s. Right, so now to start off the visualizations in the last few minutes, this is an individual trajectory, just to give you a feeling how they would look. So we plotted this in Kerr-Schild coordinates, and I want to concentrate on this plot on the left, which is the plot on the ZX plane. And you can see the geodesic starts at positive radii, goes inwards, crosses the disk, and then finally escapes to negative infinity. And what I want to stress here is that the upper half plane corresponds to positive radii, whereas the lower half plane corresponds to negative radii. And the fact why we can view it that way is that these geodesics which can cross over from positive to negative radii, so which can go through this disk, actually have the further property that they can never cross the equatorial plane somewhere outside of this disk. So they cannot go up here. So by going from the upper to the lower half plane, they necessarily change their radial sign, and they cannot go back up here again. That's why these gray curves are the horizons, and these are only plotted for positive radii. Right, so, but we're not mainly interested in individual trajectories, but rather what an observer would see. And for this, we can do the following. So we take this inner throat, discretize it, and color each point, like so. And for each point inside here, we can calculate the starting angles psi s and theta s for a source at positive infinity. So we're basically asking the question, what portion of the sky at positive infinity can our observer at negative infinity see? And to better visualize this portion of the sky, we can do the following and make one of these polar plots, where the distance to the origin is actually this polar angle theta, and the angle around the origin is this azimuthal angle psi. And with this, we basically create a projection of the northern hemisphere of the sky at positive infinity down to a 2D surface. And this blue circle here corresponds then to the equatorial plane. And what you can see is that most of what the observer actually can see up to this blue part out here is confined to a rather small area of the sky. And only by going closer to the throat boundary, this fans out and increases in size. And to study this in more detail, we did this short video here. I hope it's smooth. And here we considered rings inside this inner throat with a certain distance to the throat boundary, and mapped these over to the sky at positive infinity and see what portion you can see. And as you will see, this as we approach the throat boundary, these curves move around in the azimuthal direction and get deformed and actually fold in on themselves. And this, as it turns out, corresponds to multiple images, like these movements here. Right, and now as the last topic, basically, I want to show that we can also do the opposite, so not color the points here and map them over here, but rather paint the sky. And here we did it in the polar direction, where the sky around the axis of symmetry is yellow, and then by going closer to the equatorial plane, it becomes red, blue, and finally green. And so for an observer at positive radii, they would perceive red on top of blue. Our observer, however, gets a flipped image. So for him or her, the blue is on top of red. We can play the same game in the azimuthal direction, where for the observer at positive radii, green is on the left-hand side of yellow. And for our observer, this is again flipped. So pictures basically get flipped upside down and left to right. And for your amusement, as a last point, because I'm already going over time, is that we can now fix this RO, so the radial position of the observer and the polar position, and vary this azimuthal angle, so that we kind of create a movie for an observer which rotates around the black hole at a certain height. And the result is this little movie, where you can see that the portion of the sky the observer can see kind of moves around in circles. And with this, I already want to close and leave you with a short outlook. What's to come. So the goal, the ultimate goal, would be to create a visualization of what an actual physical observer would see. And for that, we need, of course, to consider a physical light source like a star orbiting a black hole or an accretion disk. And for a realistic image, we also need to calculate the Doppler shift and the intensity change. Yeah.
Okay, thank you very much. Questions? So I found this quite interesting and curious. So I mean, when you go inside the horizon, then I mean there are all sorts of strange causality or acausality effects.
Yes.
And I mean you have potentially closed time-like curves and so on and so forth. So I'm a little almost puzzled by that things are not even stranger, so to speak. I mean something like, I mean, how does this acausality affect what you're showing?
That's
and another related question is, I mean, in some sense, I always thought that, also that in some sense you have, if you think about Schwarzschild, I mean, you have in the inner, in the other asymptotically flat region, you have sort of time is somehow running, clocks are going backwards in some sense. That was my impression. So how does that figure into this what you're showing here?
Yeah, I mean this negative radial region is curious for a lot of reasons. So you basically would not need to flip the radial sign, but you could also flip the sign of the mass component. So you could consider it as positive radii, but with a negative mass. So that's why this region. So in this region, the black hole is actually repellent, and yeah, but
isn't that just a matter of which time direction you're considering, so to speak?
Yes,
right?
Yes.
So
yes.
I mean, for someone living in this inner region, isn't I mean, and from a certain point of view, wouldn't the black hole just look exactly like an ordinary curve, or am I misunderstanding that?
No, I wouldn't say so, because you have this radial potential would stay the same regardless of the sign of this of the time direction, so to say. So this small inner throat, which would correspond to the the shadow of the black hole in this negative R region stays the same regardless of the time direction. So yeah.
May I comment here? So Lars, if you look at the right picture, I mean the orbits of photons have to be on horizontal lines.
Yeah, yeah.
So if you are in the right situation and somewhere up in the picture, you have complicated photon orbits which go back and forth because they hit these gray walls, right? But on the left part of the orbit, negative R, you can only have one bounce point, right? So if you have an orbit which bounces, it bounces once and goes back to minus infinity. So it's going to leave this causality violating region and never come to it again. So that's why these geodesics are rather simple, right? So we're not looking at all geodesics here. We're only looking at geodesics which come in from infinity. So they really have to fit into this little aperture out there, and they just keep going, right? They have no option to stay caught in this causality violating region.
And there is no black hole for negative R, right? So this is.
And in that region, there is no black hole,
Yeah,
right?
there is no.
Yeah, it's always a naked singularity.
Yes, so this is something different, right?
So are there further questions?
Yeah, I would like to use that toy also. You had this picture where the curves are going through the ring singularity, these yellow curves.
You mean
again? Yes.
This one?
On the right hand side. No, that was fine. No, the other, the previous one.
This one.
Oh, that one, yes. So the green curve is before the plane. The yellow is after
the green curve corresponds to a positive radius of this geodesic.
Yes. Now the yellow thing circles around several times. I mean, depending on the way the green curve comes in, are there curves which circle more and more and more often? Or, I mean, it's not clear to me what's shown here.
Yeah, maybe I should have mentioned it. So actually, this is a geodesic with impact parameters rather close to the throat boundary, which circle more and more. So it's kind of as in the.
The closer you come, the more often they go around. You know?
Yes. So this is actually what's then basically shown here. When approaching this throat here, this outside, then these geodesics take way more time to reach the final.
I was wondering about this picture too. It's just numerically, it's very difficult to show more to us than this year.
Yes. So, but maybe I should have mentioned it, that this is close to the throat boundary, and most of the geodesics, so most of the field of view kind of correspond to boring geodesics, which do not much. They fall through and escape. Yes.
Yeah.
So I tried to put an interesting one, and you can see
it's very pretty. I criticism. I just want to play with this.
Yeah. Maybe what one can notice is that it stays rather a long time for small negative radii, so just below this ring, and this actually corresponds to coming close to this forbidden region in this plot. So the radial motion gets really slow, close to the gray region, and then it escapes to negative infinity.
Okay.
Yeah, close to critical point, right? Of this potential.
Yeah. So.
So may I comment that these are simulations for people who don't believe in cosmic censorship, right? Because then in this space-time we have a naked singularity, and there actually you can see this naked singularity spans a circle in the sky, and you can see through this circle what happens on the other side.
Yes, but I mean you can never see. you can never see the singularity in particular, because the singularity is in the equatorial plane, and these geodesics can never, if they
avoid
if
it.
they,
Yeah.
yeah. So if they can,
if you're already going into this kind of science fiction area, so to speak, what happens with these pictures when you make when you go to the over extreme curve? I guess a lot of the considerations have to go through, right?
yes. I mean,
Except, I mean, you won't have horizons, but you know, in principle,
you still have the ring, right? Yeah.
Calculations.
Yeah.
Just for just
for fun.
Yeah, I mean, that's a good question. I mean, the field of view, so this inner throat would increase in size, so the observer at negative radii would be able to see more and more of the sky at positive infinity. I don't know if the portion of the sky actually increases, so if the observer can see more of the sky or just with a higher resolution.
Yeah.
But you still have 2 copies of the universe, right? So you still have this throat, and you still have 2 copies and a double covering and everything, right? So it's not like when you are overcharged, you shouldn't think of this as a singular ring sitting in space-time, but you still have this other region,
yes.
which exists.
Which will, and this will, if you look at it correctly, this will persist even if you let the mass go to 0, right? I mean, that's
right. Yeah.
So
Lars, there are 2 questions. Tobias has one question.
Okay. I'm not sure how to
Rafaela.
How to invite people to talk.
Well, you can just say, Rafaela, go ahead.
Yeah. You can unmute this one.
Yeah, I already unmuted myself. Thanks. Yeah, maybe was already partially answered before the question, but I was wondering. I mean, thank you for the very interesting talk. It's really super cool. But so my question is, I mean, so somehow the setup is somehow quite specific. I mean, do you want to match it to something that can be observed in experiments, or I mean, since I mean you posed this very specific question.
Mm-hmm.
What do you want to get out of it ultimately?
I mean, yeah, this is probably nothing for like as a prediction for a real life observation, which can be compared then. But because this negative region is kind of problematic from that point of view, as that it's under the Cauchy horizon, and that you have this naked singularity there. So it's maybe more of a game and trying to visualize all features within this extended Kerr spacetime, as opposed to like trying to be able to predict some real life observation.
Tobias, I mean, I'm really saying this seriously, right? So we don't know whether cosmic censorship is true, and so this is telling you what you would see if there are there are singularities, right? Naked singularities, and they will allow you to see through things. I mean, we think that general relativity is correct, and it predicts unusual behavior. It has managed to predict black holes so far, and they've been verified. And it predicts existence of naked singularity in the form of a ring, which might be forbidden if we believe in cosmic censorship, but which might not. And so that's what you would see if cosmic censorship is wrong.
Right.
We would shoot another movie.
Yeah, thanks a lot. It's very beautiful talk. Thank you.
Okay. So if there are no further questions,
this orange curve which loops around, can you go back there?
Yes, this one. Mm-hmm.
Does it loop in this time travel zone?
No, this time travel zone would be further below, I think. Yes.
Okay,
but
thank you.
I'm not sure. I'm not sure. So I'm sorry. Maybe.
Maciek, if I remember correctly, the time travel zone is a torus which touches the ring, right? But I think that this. So depending upon the parameter, it might very well cross the travel zone ring. If you're very close, it might actually hit it, but it's going to leave it just by this argument of looking at the plots of the forbidden zone in the potential.
I don't remember the shape.
Yeah.
Okay, so well, so maybe this is a good point to close. And so thanks again for this very interesting talk, and there's very curious things. But I have to say, even the very extreme mass equal to 0 case, I think is actually not at all unimportant. It's actually, I believe, it's actually very important, even that seemingly simple extreme case. So we should thank all the speakers and also all the local organizers for this technically advanced version of the CRS.
Thank you very much, Thomas, for all your help.
Yeah, it's very smooth. Thanks.
Yes, thank you.
Thanks a lot for the kind words.
So hopefully we'll see each other in the flesh next time, so to speak.
Thanks a lot, everyone, for coming. And yes, as Lars said, see you next year at CES. We'll send information whether it's going to hopefully in presence, if not, again online.
George, you said something about talking afterwards.
Yes. So now we're going to leave the meeting. And Lars, can you open a Zoom? Can you send us a Zoom invitation for another meeting?
Yeah. Okay. So I'll do that once immediately after I leave this.
Okay.
one.
Great.
Okay. I'm very ignorant, so I shut down this thing.
Yeah. You exit and you look up at your email and you click on the link.
Yeah. Okay. So I'll do that in 1 second.
Bye, everyone. Okay. Thanks.
Bye.
Thanks a lot.
Thanks again, Thomas. Bye-bye.
Glad to be of help.
Okay, Thomas, so I should be clicking on this, and then which format will it produce? Do you know?
It will produce M4A video formats. That's
maybe stop the live screen.
Okay. Yeah. So this